Okay, Chemistry 3101, Organic Chemistry 1. Our first chapter is nothing more than a review of general chemistry, electrons, bonds, and molecular properties. So if you took General Chemistry 1 and General Chemistry 2, which are prerequisites for this course, if you took those at UCCS, General Chemistry is Chemistry 1401 and 1411. Those are the two general chemistries that you need in order to take organic chemistry. Well, let's move on and let's start and talk about what organic chemistry is. It says that organic chemistry is the study of carbon-containing molecules and their reactions. So looking at carbon-containing molecules. So if you go back to general chemistry, you would have learned about periodicity, things like ionization energy, electron affinity, electronegativity. And you would have looked at those concepts from the point of view of the entire periodic table, the S block, the P block, the D block, the F block. So you would have talked about transition metals and lanthanides and actinides, semi-metals, non-metals, all those things. You would have spent a lot of time looking at the entire periodic table. However, you need an entire year to study one element on the periodic table, carbon, one single element. And we have a whole year dedicated to studying that one element and the reactions that pertain to that element. And so that is what organic chemistry is, just the study of carbon. And if you're wondering, well, why is carbon so special? Well, carbon can do a lot of things that other elements can't do. It can form bonds to itself. There are some elements that can do that, but it can form single bonds, double bonds, triple bonds. And it can also bind to a wide variety of elements like oxygen, nitrogen, phosphorus, silicon, sulfur, the halogens, fluorine, chlorine, bromine, and iodine, and other elements as well. So what happens to a molecule during a reaction? Well, you would have learned when you talked about reaction rates, for example, you would have discussed that molecules collide, and when they collide, bonds are broken, so bonds are formed, bonds are made. So we break bonds and we make bonds. And you can see that what's going on in this reaction here is that it's showing the formation of a bond and the breaking of a bond simultaneously. And if you're not sure what I mean by that, well, take a look at this. If you look at this arrow here, and I'll highlight it in green, if you look at this arrow, it's actually showing a bond being formed. How do I know that? Because in the product, this compound here, you can see there is a bond between the oxygen and the carbon. And so that curved arrow that I have highlighted in green represents the flow of two electrons, one lone pair from that hydroxide over to the carbon to make a bond. But we know that carbon cannot have 5 bonds. Carbon is what we call tetravalent. Carbon always forms 4 bonds unless it has a charge or is a radical. And so we cannot have 5 bonds to a carbon. And so we are also breaking a bond. And you see that this curved arrow here represents the breaking of a bond, right? You don't see this bond is not present over here. There's no bond between the carbon and the iodine. And one of the questions that we want to ask ourselves is, why does a reaction like this even happen? Why does it happen? Why does the hydroxide react with this compound? This is called iodomethane to make methanol, which is used as a fuel. If you've ever made fondue, it is used as fondue fuel. Anyhow, in the iodide ion. Why does that even happen? Well, we need 2 semesters to answer the question. And the 2 semesters are Chemistry 3101, in which you are presently enrolled, and Chemistry 3111, which is Organic Chemistry 2. And really, when you boil it down to its simplest bit, organic chemistry is focusing on electrons. It is the study of electrons and what they do. Watching electrons move in a reaction and understanding why they do what they do. So we're going to spend a lot of time focusing on electrons. Well, you've probably heard of things that are organic and inorganic. And how do we distinguish between things that are organic or inorganic? Historically, people thought that compounds that were organic were things that came from plants and animals, okay? And historically, people thought that everything that was inorganic came from a mineral. Now that's not entirely true. Okay, there's a mineral. Okay, that's not entirely true, and I'll get into that, the history of that in a second here. So historically, okay, this is what people thought, plants and animals. But what happened was a scientist by the name of Friedrich Wöhler, Friedrich Wöhler did a famous experiment where he took ammonium cyanate, which is an inorganic compound, and he just heated it up, and he ended up making urea, which is one of the organic compounds found in urine. And so this dealt a huge blow to the scientific community because people believed in something called vitalism. And vitalism was an idea that in order for an organic compound to exist, there had to be some kind of outside vital source that was partially or fully responsible for making an organic compound. And so again, what Wöhler did was he took something that was inorganic, the ammonium cyanate, and he made something that was organic. And people thought, well, there's no way to do that. And so he disproved that by this experiment. In fact, he wrote a letter to one of his colleagues and he said, I've synthesized or I've made urea without a kidney, without the aid of a dog or a man. So basically they had isolated urea from urine in dogs and in humans and probably other animals as well. However, that is what he said in his original letter to his colleague. And so people started to get the idea that vitalism was not the reality and that organic compounds could be made from things that are inorganic. And so this idea seemed to vanish over time. And so why are organic compounds so important? Well, organic compounds are found everywhere. They're found in natural fibers like wool, silk, cotton. They're found in synthetics like polyesters and nylon. So you can see that they're found in clothes, things like nylon or what else, Kevlar, polyester. What's another one that I'm trying to think of? Gore-Tex, would be a great organic polymer. So there we go. Pharmaceuticals, so any kind of marketed drug, whether it's Vioxx or Singulair or amoxicillin or Cialis or any kind of Lipitor, any kind of prescription drug that's a small molecule, it's going to be an organic compound. Organic compounds are found in foods, and so if somebody says, these bananas are organic, well, I would hate to eat an inorganic banana. That doesn't sound very appetizing. Plastics are also organic, and plastics are just ubiquitous. They're everywhere. Everything I'm looking at right now seems to be made of plastic, except for maybe my watch. Anyhow, so what else here? Organic compounds contain carbon atoms. Now, if you're very astute, you might have noticed an exception on here. There is an exception to that because the cyanate ion, okay, so that's OCN minus, that's a cyanate. So cyanate, it contains carbon. However, it is not considered organic. There are a couple other examples. Let's see here. Cyanide. So cyanide, it contains carbon. It is also not considered organic. And then I'd say the carbonate ion. So carbonate and bicarbonate ions. So carbonate. Those are not considered organic. So we'll put here, not organic. Not considered to be organic. All right, so organic compounds contain carbon atoms. Well, let's move on to structural theory. And what it says here is that by the mid-1800s, it was first suggested that substances are defined by a specific arrangement of atoms. So we have a substance, it's made of atoms, but they're put together in a specific arrangement. So the way that they're connected is of importance. It says here, why is a compound's formula not adequate to define it? Let's say you had a compound and it had a formula like C2H6O. Why is this just simply not enough information to describe the compound? Well, the reason why is because there's a couple of different ways in whereby you can put these atoms together to make a compound. In fact, there's two different ways you can put C2, 2 carbons, H6, 6 hydrogens, and 1 oxygen together to make a compound. You can make this compound, dimethyl ether, and you can make this compound ethanol. We call those compounds constitutional isomers. Why? Because they have the same molecular formula, but they have different connectivities or different structures. And you can see that they have different physical properties. Dimethyl ether has a boiling point of negative 23 degrees Celsius. That means if you go outside when it's negative 22 degrees Celsius, that is extremely cold outside, or at least I consider it extremely cold. Somebody in Antarctica might not think that, but it's extremely cold. That means that even at negative 22, the dimethyl ether is going to be a gas. Okay, it's not going to condense into the liquid phase, whereas ethanol, which is the alcohol found in Budweiser or wine or Goldschlager or schnapps, okay, whatever, and found in any kind of alcoholic beverage, it has a high boiling point of around 78.4 degrees Celsius, high compared to that of the dimethyl ether. And so something like dimethyl ether is used as a propellant for aerosol cans, whether it might be hairspray or a spray paint or something like that. That is what's used to force the hairspray out of the can. Okay, whereas again, ethanol is not only used in alcoholic beverages, but it has many different uses. It can be used as a solvent in a reaction. It is also found as an additive in gasoline. So the idea of this slide is that we have constitutional isomers, compounds with the same molecular formula, but different structures, okay, different structures. I'll give you another example. If anybody here has studied biology before, and I'm going to assume that many of you have, you might have seen this before, C6H12O6. Could anybody tell me what that formula is oftentimes used to represent? It's an organic compound.
Glucose.
Yeah, it would be glucose, yeah. So glucose. So if you unmute your mic, like the way to avoid the feedback is, I guess, to turn it down before you do it. But anyhow, yeah. So glucose. However, C6H12O6 can be the formula of many different compounds. It can be allose, it can be talose, it can be aldose, it can be mannose, it can be xylose, okay? So there's many different sugars that have this same molecular formula. So we'll put here glucose, etc. Okay, there's many different compounds that have that formula. And so to just simply say something, we just say, I'll give you the molecular formula, and then you must know the identity of the compound. Not true, okay? Because there are many different ways whereby you can connect either of these molecular formulas. So you can connect them to make different compounds. Okay. Give me a thumbs up on the chat if you follow me. Let's see here. Is there a thumbs up tool here? Let's see, there's an emoji tool. Let's try that. Oh, here we go. There's a smile. There we go. Oh, I see. Here. Good. Thanks, Alexandria. So Alexandria, Luke, you follow me on the idea of constitutional isomers. Because I think one of the first problems that we're going to look at in the slides is you take a molecular formula and you try to draw all the different constitutional isomers. Okay, and don't worry, I'm not going to give you C6H12O6. I'll give you a simple molecular formula, and then you try to come up with all the possible ways that the elements can be connected together. Well, besides carbon, what are the elements that are going to show up the most in this class? The ones that are going to come up the most, I'll be honest, would be nitrogen and oxygen and hydrogen. Other elements are going to show up, of course, the halogens. You need to know all the halogens, fluorine, chlorine, bromine, and iodine. And yes, we're going to look at things like phosphorus and sulfur and silicon. And I'm trying to think, did we look at anything besides that in this class? Probably not really. We probably stopped somewhere around there. So yeah, carbon can bind to a lot of different elements, but the ones that we're most interested in are going to be nitrogen, oxygen, hydrogen, and the halogens. Okay, and so it's a good idea for you to learn and to memorize, for now, how carbon binds to these elements and how these elements bind to other atoms. Okay, and so we say that carbon, generally speaking, is tetravalent. Carbon, generally speaking, forms 4 bonds. Okay, and sometimes it can be 3 single bonds, the way it's drawn here, but it could also be, 2 single bonds and a double bond. It could be a single bond and a triple bond, etc. But the idea is that carbon will form 4 bonds. Nitrogen, however, Nitrogen is what we call trivalent because it generally forms 3 bonds, so three bonds, and it also normally has 3 bonds and 1 lone pair. And so you might remember that from compounds like ammonia, for example, NH3. The nitrogen has 3 single bonds, 1 to each hydrogen, and a lone pair. And I'm sure that that's a Lewis structure you would have seen in your General Chemistry 1 and probably your General Chemistry 2 class as well. Next, we have oxygen, and we say that oxygen is divalent. It, generally speaking, forms 2 bonds. It usually has 2 bonds and 2 lone pairs. And I know what you're thinking. The most classic example of that would be water, right? The oxygen in water has 2 bonds and 2 lone pairs. And I'm sure that that's a Lewis structure that everybody has seen and knows the molecular geometry of the water molecule is bent. And we'll get into that later on in this chapter. And the last one are the halogens, whether it's fluorine, chlorine, bromine, or iodine, and the hydrogen atom as well. Those are all monovalent, meaning that they only form 1 bond with, one bond with another atom. Now, I know that you learned exceptions to that rule. In General Chemistry 1, you would have seen things like iodine heptafluoride or something like that, where the iodine or a bromine can be polyvalent. However, you will never, ever, ever see that in organic chemistry. It doesn't mean it doesn't exist, but it just doesn't come up in this class. Now, all of the halogens will always form 1 bond, and then they'll also always have 3 lone pairs, whether it's in a compound like HF, hydrogen fluoride, or if it's in chlorine, Cl2, right? Halogens always form 1 bond and have 3 lone pairs. We're never going to see a polyvalent halogen in this class. And there you go. Now, you might need to memorize this today. Maybe you're going to say, well, once the lecture's over today, I'll spend some time memorizing this. And that would be fine. There's nothing wrong with memorizing. However, something that you'll discover is that once you're done completing all the practice problems in the textbook, you will have this not memorized. It will be ingrained in your memory for the rest of your life. Okay, you will see so many carbons in this class, so many nitrogens and oxygens and hydrogens and fluorines, etc., that you will not have to think twice about this probably after the first chapter. It tends to become rather natural to students once they've done enough practice. Well, with all that in mind, who wants to give a practice problem a try? Even if you don't, we're going to do it. So let's see here. It says draw all the constitutional isomers with the following molecular formula. We've got 3 carbons in the first one, so this is question 1.1a. 3 carbons, 7 hydrogens, and a chlorine. First of all, we know that carbon, generally speaking, forms 4 bonds. Hydrogen forms 1 bond, and chlorine forms 1 bond, and then has 3 lone pairs. So with all that in mind, what are my options here? Well, the first thing that I notice is just by kind of process of elimination, I can see that hydrogen and chlorine cannot be part of a chain. They cannot be part of a chain because in order for them to be part of a chain, in order for an element to be in a chain, it has to be able to form 2 bonds. But hydrogen and chlorine never form 2 bonds. They only form 1 bond. So these can not part of a chain. They can't be part of a chain. And therefore, if I have, all these different elements, that means the only elements that I can put together in a chain would be the carbons. I can definitely put carbons together in a chain like this, 1, 2, 3, like this. Okay, well, what do I know about carbon? Carbon has to have how many bonds? Who could tell me? Not a trick question. I don't like to ask any trick questions. How many bonds for carbon? Thanks, Luke. Absolutely. 4. And so what we could do is we see that the carbon in the middle already has 1, 2 bonds. So we could complete that carbon with 1, 2 more bonds. And the carbon on the far left and the far right, well, they each have 1 bond. You can see that this carbon has 1, this carbon has 1, and therefore we can fill them up to having 1, 2, 3, 1, 2, 3, and that works out because now we have 1, 2, 3, 4, 5, 6, 7, 8 lines off of these carbons. They have nothing bound to them. And we have a total of 8 atoms that can only form one bond. So I'm going to start by putting in hydrogens. 1, 2, 3, 4, 5, 6, 7. And I've got a chlorine. I'm going to put that down here. I'll put the chlorine right there. And so there we go. There's our first constitutional isomer of C3H7Cl. Could anybody unmute their mic and describe to me how I could make a second constitutional isomer from this formula?
Well, you can replace the Cl with one of the H.
Mm-hmm. And then where would I put it?
You can just replace with like any of the H.
Okay. Does anybody else have another idea?
Well, the first. Go ahead.
Oh, I was gonna say you could put the Cl with the and bind it to the second carbon in the chain.
Okay, yeah, let's start with that. So if I put the 3 carbons in a row, and then I draw a single bond so that they all have 4 bonds. And then instead of having the carbon on the end, or sorry, the chlorine on the end, if I put the chlorine in the middle, then I have a new constitutional isomer, don't I? Because the compounds have the same molecular formula, but the connectivity or the arrangement of the atoms is different. If I was to number these carbons just for fun, if I called this 1, 2, 3, and I called this 1, 2, 3, you see that in the first isomer, the chlorine is on carbon 3, whereas in the second one, it's on carbon number 2. And thus, these are 2 unique constitutional isomers. Now, what I heard somebody say is, well, couldn't you take and put the chlorine anywhere else? So let's say if I put the chlorine here, okay, like this, would this be a new constitutional isomer? Yes or no? Is this a new connectivity? No, this is not a new connectivity. This structure that I've just drawn is the exact same as this one that I have right here. These two are identical. Now, why is it? You might be thinking, well, the chlorine is in a different spot. It is not. Remember that there is free rotation around a sigma bond. A sigma bond can rotate. Pi bonds cannot rotate. However, a sigma bond can rotate. And so since that bond can rotate, that means that whether I put the chlorine at the far end where I have it here, or if I was to move it, let me just erase it here. If I put the chlorine over here, I still have the exact same compound. These 2 compounds are identical. All right, and so in fact, let's delete this one because we've drawn the 2 possible constitutional isomers having the formula of C3H7Cl. We're done, as a matter of fact. It's over. We completed the problem. There's no other way to put these together. If you're wondering, well, hold on, Mr. Dion, what if you did this? 1, 2, 3. What if you put the chlorine over here on the far left? It's still the same connectivity. The way the atoms are connected is no different. If you were to take an axis here and rotate this compound 180 degrees, you'd end up here. It'd be the exact same place. Okay, and so there are only 2 possible constitutional isomers for this molecular formula, and we've drawn both of them. I'm going to delete that. There we go. And later on, we're going to learn nomenclature, or how to name organic compounds. And what you'll discover is that when you name compounds, if you come up with a different name, then that tells you that the two compounds are different. But if you name 2 compounds and you get the same name, then they're the same. This first compound, this would be called 1-chloropropane. And this compound here would be called 2-chloropropane. And I'll explain that more later on when we cover nomenclature in chapter 4, but I'll just scribble it down there in the meantime. Okay, C4H10. How many different ways can we connect these atoms? Same rationale. We know that carbon forms 1, 2, 3, 4 bonds, and hydrogen forms only 1 bond. Therefore, what's our options? The only atoms that can be connected together are the carbons. And so that means we have to have all the carbons being connected to each other. So we'll put all 4 of them in a row, and then we're going to draw enough lines so that every carbon will have 4 bonds. And look, I have 10 lines coming off of the carbons, and they're not bound to anything. So now I'm going to put on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens like that. So there we go. That's one constitutional isomer. I'll just throw it out there to my students. Is there another way to organize the carbon atoms? I'm not going to ask about the hydrogens because they can only have 1 bond, but is there another way that I could organize the carbon atoms? Is there another way I could put those together? Yeah, could anybody tell me, unmute their mic and tell me? Yeah, exactly. So I see that Clinton uploaded a structure in the chat. He's absolutely right. He's saying, well, you've got 4 carbon atoms. And so what if you put just 3 in a row like this, and then you made a branch like that? Have one of them coming off as a branch. And that is absolutely correct. Then you can see that these 3 carbons only have 1 bond attached to them. And so they all need 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So 3 times 3 is 9. And this carbon has 3 bonds attached to it. Thus, it only needs 1. And that makes up our 10th hydrogen. This compound is called butane. It's the same butane that's found in a Bic lighter. And this compound is called isobutane. Isobutane. It also has another name, which is 2-methyl propane. Again, don't worry about the names. The names, so nomenclature, write that down here. Nomenclature, that's covered in chapter 4. I'm just throwing it out there just so you get the idea of the names in your head, just so you hear some organic compound names. All right. Good. Give me a thumbs up if you follow me on constitutional isomers. And even if I follow you on the rationale, I'm going to have to practice it. If you're thinking I have to practice, that's totally normal. Everybody has to practice. I have to practice. It's totally normal to have to practice organic chemistry. In order for somebody to hear it the first time and just say, well, I understand that. I know everything after hearing him talk about it, that would be impossible. A person has to practice organic chemistry. Okay, great. So constitutional isomers. You know, depending on who you had as an instructor for general chemistry too, some of you might have seen this in a section on organic chemistry and general chemistry too, but some teachers don't cover it, and so there we go. But you all would have seen Lewis structures, so these are nothing more than Lewis structures. Okay, well, let's talk about covalent bonding. Going back to your general chemistry 1 days, you would have learned about 2 types of bonding. So bonding, you would have learned about ionic bonding, and you would have learned about covalent bonding. And in organic chemistry, we're mostly concerned with covalent bonding. And covalent bonding is the bonding that occurs between 2 nonmetals. So we'll just write down here, nonmetals, plural, 2 of them. Whereas ionic bonding is not that. Ionic bonding is what occurs between a metal, and a non-metal. An example of an ionic compound would be something like sodium chloride, whereas a covalent compound would be something like CO2. Because sodium is a metal, chlorine is a non-metal, that makes it an ionic compound, whereas carbon dioxide is made from carbon and oxygen, both of which are in the P block. They're both non-metals, and therefore make a covalent compound. Well, covalent compounds are formed from covalent bonds. So what exactly is a covalent bond? If you go back to this question, every single one of these bonds, and I mean every one of them, these are all covalent bonds. Every single bond that we drew on this entire slide was a covalent bond. So what is a covalent bond exactly? It says here that a covalent bond is a pair of electrons that are being shared between 2 atoms. The simplest possible example I can think of a covalent bond is shown here. This graph here, which is a plot of energy versus internuclear distance, shows the formation of a covalent bond between two hydrogen atoms. These are hydrogen atoms, and this is a hydrogen molecule. Hydrogen molecule, right? Hydrogen molecule is H2, and the hydrogen atom is simply H. How many electrons does a hydrogen have? It has one electron. And so if we have the two hydrogens separated by a large distance, it could even be up to, infinity, really. Okay, well, as we start to bring those hydrogen atoms together, there's sort of three things that can take place. You can have the repulsive forces as you bring them closer together. The repulsive forces between the two electrons, one from each hydrogen atom. The repulsive forces between the protons in each of the nuclei. The repulsive forces between the two protons in the nucleus. And then you can also have an attraction between the electron in one hydrogen and the proton in the nucleus of the other. And so what happens is you bring those hydrogen atoms closer and closer together, they start to minimize the repulsive forces between them and maximize the attractive forces between them. And they start to decrease in energy. The energy starts to drop until they get to what you would call the most stable distance between the two atoms. And this distance has a distance of 0.74 angstrom. Remember that an angstrom is equal to a 10 to the negative 10 meters. So it's a very small distance, but once they get to that 0.74 angstroms, they release 436 kilojoules per mole of hydrogen molecules. And so since the delta H is negative, energy is released, you get something that's more stable. It also tells you that if you had 1 mole of hydrogen molecules, in order to break them apart and to convert them just into hydrogen atoms, that would cost you 436 kilojoules of energy. And so essentially, a covalent bond is nothing more than the sharing of electrons between two atoms to form a stable bond, which is exemplified here by the formation of a hydrogen molecule. All right, if you were unsure about protons and electrons and neutrons, well, let's review some of that. Hopefully you remember from general chemistry that a proton has a +1 charge and it resides in the nucleus of the atom. A neutron is also found in the nucleus of an atom. However, it is neutral. It has no charge. Now, if you're wondering, why didn't you bring up neutrons in that covalent bonding example? Remember that a hydrogen atom has no neutrons in its nucleus, doesn't it? A helium atom does, but a hydrogen atom has no neutrons in the nucleus, only one proton. And then, of course, we move on to our favorite particle, which has the particle wave duality, and that is the electron. And an electron has a -1 charge, and it resides in an orbital outside of the nucleus. And we're going to talk about s orbitals and p orbitals a little bit more in today's lecture. Now, what are the electrons that we're most concerned with or most interested in organic chemistry? The ones that we're most interested in would be valence electrons. And those are the electrons found in the outermost shell. Remember that, for example, if you form a sodium cation, sodium has one valence electron. It's found in group 1A. When sodium loses its valence electron, it forms a sodium +1 cation. And so this electron that I have here, that's the valence electron. So sodium likes to lose one valence electron. And so that would be something that you should have seen in General Chemistry 1. If we look at carbon, for example, and you should know how to write out an electron configuration. If you look at the periodic table, you see that carbon has a total of 6 electrons. And so we write out the electron configuration 1s2, 2s2, 2p2. But which ones are the valence electrons? Out of all 6 of these electrons, 1, 2, 3, 4, 5, 6, could anybody tell me which ones are the valence electrons? Exactly. The 2s, exactly, the 2s2 and the 2p2. The ones that are in the orbitals that have a principal quantum number of 2. Exactly. So these ones here, these are the valence electrons. Valence electrons. And that is why when we write the Lewis structure of carbon, we write it with 1, 2, 3, 4 electrons surrounding it because it has 4 valence electrons. And thus, when we're looking at bonding, we focus on valence electrons. Why can carbon form 4 bonds? Because it has 1, 2, 3, 4 valence electrons. 4 valence electrons, 4 bonds. You can always calculate the number of valence electrons by looking at electron configuration. If you go to the group 4A, you see that all of those elements have 4 valence electrons, and thus they can have 4 bonds. If you look at nitrogen, it's in group 5A, thus it has 5 valence electrons. Let me just scribble it up here. So we'll write nitrogen, and then we'll put 1s2, 2s2, 2p3. So we have 1, 2, 3, 4, 5 valence electrons for nitrogen. I'll scribble oxygen down here. So oxygen is 1s2, 2s2, 2p4. It's in group 6A. Oops. Group 6A. And it has 1, 2, 3, 4, 5, 6 valence electrons. So just by looking at a group number, you can determine the number of valence electrons in an atom. And this is something that we're going to look at many, many times throughout the course. And so it won't take you long to memorize that oxygen has 6 valence electrons, fluorine has 7, etc., etc. Let's talk a little bit more about Lewis structures. Lewis structures are extremely important in organic chemistry. We use them not all of the time to represent molecules, but they do come in very handy from time to time. So how do we put a Lewis structure together? Well, we got a couple of rules here. First rule is that we're going to draw the individual atoms, and we're going to put dots around them to represent the number of valence electrons. And then we're going to put the atoms together so that they share those pair of electrons to make complete octets. An exception to the octet rule, except hydrogen, which only needs a duet of electrons. It only needs to be surrounded by 2 electrons because it only has the 1 s orbital available to it. Hydrogen can only ever form 1 bond. No exceptions to that rule. Well, let's take a look at ammonia. We saw that nitrogen was in group 5A, and so it has 5 valence electrons. Remember that once you cover all 4 sides and then you have the 5th electron, it has to go into a pair, which makes a lone pair. A lone pair is a lone pair. They're paired up already. Thus, the lone pair will not be used to make a bond. But we have 3 unpaired electrons that can make bonds. Excuse me. Then we look at the hydrogens. They're all found in group 1A. They all have 1 valence electron. And so they're all capable of forming 1 bond. Therefore, how are we going to put them together? Well, you see the arrangement right here. That you have the nitrogen surrounded by the 3 hydrogens. And you can connect the dots, so to speak, here and here and here. So that the nitrogen has 1 lone pair and 3 bonds. Is the nitrogen surrounded by 8 electrons? Yes, let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Remember that each one of these bonds contains 2 electrons. So again, 1, 2 from the lone pair, 3, 4, 2 electrons in this bond, 5, 6, 2 electrons in this bond, 7, 8, 2 electrons in that bond. And so the nitrogen has a complete octet. Do each of the hydrogens have 2 electrons surrounding them? Yes. Each hydrogen has 1, 2 electrons surrounding it, 1, 2, and 1, 2. And so everybody is happy in this Lewis structure. And that would be the proper Lewis structure for ammonia. I know that in some books, they'll sometimes use a Lewis structure like this, where they represent a bond being 2 electrons between 2 atoms like that. Do not draw that. I think that is ugly, and it is never used anywhere in our textbook or in any good organic chemistry textbook. So I wouldn't use that. Okay. Well, with all that information in mind, and I put the rules here again, let's try drawing some Lewis structures for the following compounds. One thing that I didn't mention on the last slide is tallying up the total number of valence electrons, which is very handy. Let's try doing that for the first example. C2H4, question 1.8. Well, how many total valence electrons do we have in C2H4? How many valence electrons are there in a carbon? Not a trick question. Could anyone tell me? Something I've gone over already today. How many valence? Yeah, exactly. Right? So we have 4 valence electrons for a carbon. And there's 2 carbons. So 4 times 2, that gives us 8. How many valence electrons are there in a hydrogen? There's only 1. So we have 1 times 4 and 4 times 2. So 4 times 2 is 8. And 1 times 4 is 4. 8 plus 4 gives us 12 valence electrons. And so what can we do? Well, we know that hydrogen can only ever form 1 bond, but carbon, however, can form 4 bonds. And so what we'll do is this. We'll draw a carbon and we'll connect it to, why don't we put the 4 valence electrons around the carbon? We'll draw another carbon and we'll put 4 valence electrons around it. Then we'll connect 1, 2 hydrogens to this carbon. We'll connect 1, 2 hydrogens to this carbon. Well, you can see that the hydrogens all have 1 bond, but the carbons do not have complete octets. You see that this carbon is surrounded by 1, 2, 3, 4, 5, 6 electrons. And so what do I want to do with the 2 electrons here and the 2 electrons here? Could anybody tell me what would be my best course of action here in order to complete this Lewis structure? And feel free to unmute your mic. Yeah,
can we do a double bond?
Absolutely. Absolutely. We want to make a double bond. I'm going to erase these just to make it a little bit prettier. So there we go. We're going to make a double bond like this. Now that's kind of an ugly Lewis structure. I can make it a lot more pretty than that. So I'm going to erase this and I'll redraw it in the proper way. Make it look a little nicer. Oops. Like this. So we have a double bond between the 2 carbons. There we go. And this molecule is called ethylene, used as a fruit ripener. So ethylene. Anyhow, let's tally up the number of electrons to make sure that there's 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There you go. We've used up all of the electrons. Is each of the carbons surrounded by 8 electrons? Yes. Let's just look at this one. 1, 2, 3, 4, 5, 6, 7, 8. The same applies for the carbon on the right. And so this is a perfectly legitimate Lewis structure. It's the only Lewis structure that you can draw for this formula. Excuse me. All right. Well, let's move on to the next one. CH3OH. You can see how this one, they didn't write CH4O. They didn't put that. They actually put it in this order. And the reason why they do that is to try to help you rationalize that the carbon is bound to the oxygen and then bound to the hydrogen like this. I'm kind of going ahead here like pretty quickly, but the idea is that this is what we call a condensed formula, which tries to give you some, or tries to show you the connectivity of the atoms. If we tally up the total number of valence electrons here, we have 4 plus 3 for the 3 hydrogens, plus 6 from the oxygen, plus 1. So that gives us 8 plus 6, which gives us a total of 14 valence electrons. Well, if we put the carbon and we attach it to the oxygen, and then we put the hydrogen over here, we've only used up 4 electrons, so we have 10 left to go. The oxygen has 2 bonds attached to it, but remember that oxygen always has 2 bonds in 2 lone pairs. Now we've gone from using up 4 to using up 8 of the electrons, and we only have 6 left over. But we also know that carbon always forms 4 bonds. 1, 2, 3, and here's the 4th. We have 3 more hydrogen atoms, and we're going to put them on the carbon like this. And now we have a completely legitimate Lewis structure for this compound. And this is methanol, which I mentioned at some point today. I don't remember exactly, but I know I brought up methanol, which is also known as wood alcohol. Wood alcohol. But there you go. These are Lewis structures, and that's just a little review on how you put Lewis structures together. Any questions about Lewis structures? And of course, you're going to need to practice them, because I will ask you some Lewis structures on your first quiz. Draw the Lewis structure of this, or draw the Lewis structure of that. Any questions about Lewis structures? No? Okay. All right. Well, don't hesitate to stop me at any point. You can either type in the chat, as I'm doing, or you can unmute your mic at any time. You're never offending me by asking me a question. I like answering questions about organic chemistry. Well, let's try something else then. Let's try formal charges. This is something that you would have seen in General Chemistry 1. When you covered Lewis structures, they would have taught you how to assign formal charges to atoms within a Lewis structure. I can show you a very fast way to do it. It says here you have to remember what an anion is and a cation is. An anion that you would have seen a lot in general chemistry would have been the chloride ion, for example. And a cation you would have seen a lot would have been the sodium ion to make sodium chloride. And how do you know that these have formal charges of negative and positive respectively? Well, there's a formula that we use. It says here formal charge is the number of valence electrons, which you can get from the group number, subtract the number of non-bonded electrons, subtract the number of bonds. I have a much easier formula, which is this. I learned it from a colleague of mine. Its formal charge is equal to the number of valence electrons, subtract the number of sticks. We'll just put here, subtract the number of sticks, which is the same thing as bonds, subtract the number of dots, which are non-bonding electrons. So valence electrons, subtract number of sticks and number of dots. If you're just sitting there wondering, what do you mean by sticks and dots? Let me show you very quickly. Let's say we have AlH4. What is the charge on the aluminum? Could anybody tell me? And I recommend that you have a periodic table with you when you're studying organic chemistry. Could anybody tell me how many valence electrons aluminum has? Not a trick, just take a look at the group number. If you go back a couple of slides, yeah, thanks, Angel. Absolutely, it's 3 because aluminum is in group 3A. So we take the number of valence electrons. How many sticks are surrounding the aluminum? 1, 2, 3, 4. So subtract the number of sticks. How many dots? Do you see any dots around the aluminum? I don't see any dots. I see some dots over here, but that's another question. So we've got subtract 0 dots. 3 minus 4 minus 0 gives you -1. Therefore, the charge on the aluminum is negative, -1. If we look at the hydrogen, hydrogen has 1 valence electron. It's surrounded by 1 stick. It has no dots on it. And therefore, 1 minus 1 minus 0 gives you 0. And so there is no charge on any of the hydrogen atoms. Could anybody tell me what the formal charge on the oxygen is in this problem? Yeah, thanks, Guyana. Yeah, you're absolutely right. It's +1. Did anybody else get +1? Great, great, excellent. Okay, same rationale. And if you feel like I'm going too slow, we'll speed up later on once we get into new content. But oxygen has 6 valence electrons. Subtract 3 sticks, subtract 2 dots, gives you +1. And so we have a +1. That's not a very good positive. No, that's not good either. There we go. So we have a +1 on the oxygen. If we look at the hydrogens, same rationale, 1 valence electron, subtract 1 stick, subtract 0 dots, gives you 0. Let's try this next one. Could anybody identify a formal charge in C? Just unmute their mic and tell me where it would be, on which atom, what the charge would be. Give you a second to think about it. Are there any formal charges in this one? I think there is. I think there's one formal charge in C. Yeah, thanks, Andrew. Yeah, there's a -1 charge. On which element? Exactly. There's a -1 charge on the nitrogen. Thanks, Luke. Great. Yeah, absolutely. If we look at the nitrogen, nitrogen has 5 valence electrons. Subtract 2 sticks, subtract 4 dots, that gives you -1. And so the nitrogen has a -1 charge. The hydrogens all have 1 bond, so they have no formal charge. And the carbons both have 4 valence electrons. Subtract 4 sticks, 0 dots, gives you 0. Okay, and what about the last one? Did anybody find a formal charge on the last one? Any formal charges anywhere in this last one? I'll give you a clue. There is one somewhere. Yeah, absolutely. Absolutely. There's a +1 charge in the molecule, isn't there? Which atom is it on? Perfect. Perfect. Thanks, Clinton. Absolutely. You're all correct. Yes, there's a +1 charge on the oxygen, isn't there? Oxygen has 6 valence electrons. Subtract 1, 2, 3 sticks. Subtract the 2 dots. 6 minus 3 minus 2 gives you +1, and therefore the oxygen has a +1 charge on it. There we go. Great. Excellent. What do you think of formal charge? Not too bad? Give it a thumbs up. Formal charge. Let's see here. I'm working on the emoji thing here. Yeah, it's the formal charge of the entire molecule. So in order to evaluate the formal charge of the entire molecule, you would look at the whole thing, right? Since you have +1 and no other charges, it's +1. Yep. But we want to be able to identify formal charges on specific atoms in organic chemistry. I know that in general chemistry, sometimes they'll do this. So depending on where you study general chemistry, sometimes they'll do something like this. They'll put an ammonium ion, and instead of writing the positive charge next to the nitrogen, they'll put a bracket around it like this, and then they'll just say +1. That doesn't really work in organic chemistry. You've got to be able to identify where the formal charge is. So you would want to write out the ammonium ion, NH4, right? And then you would want to put the positive charge here. So you got to know where the charges are. Okay. Okie dokie. All right. Why don't we cover one more section and then we'll take a short break. Okay, so, and I mean maybe like a 10-minute break or something, just to get a drink of water. Okay, why don't we talk about polar covalent bonds? So polar bonds, and this goes back to, one of the trends of the periodic table that you would have learned in General Chemistry 1 is electronegativity. Electronegativity. Could anybody tell me what the most electronegative element on the periodic table is? Does anybody know which one it is?
Is it fluorine?
Yeah, absolutely. It's fluorine. Yeah, fluorine gets the gold. So we'll circle it in yellow. We'll put here gold medal. Okay, it's first place. But one thing I want you to remember, because we look at fluorine some in organic chemistry, but we see oxygen every waking moment of organic chemistry practically. And so I want you to remember this. You heard it here first, folks. Oxygen takes the silver metal, or second most electronegative. So don't discount oxygen. Oxygen is very electronegative. Yes, fluorine is the king of the castle. It has the highest electronegativity, but oxygen is still very electronegative with an electronegativity of 3.5. So if you're wondering, what is electronegativity? Or I forgot what it was, what's the difference between electron affinity and electronegativity? Well, electron affinity is the measure of how much a free atom wants to take an electron. Like, for example, a non-metal like chlorine would have a higher electron affinity than a sodium, okay? Whereas electronegativity is a measure of how strongly an atom wants electrons in a bond. Okay, so electronegativity has to do with bonding. We'll underline here shared, right? Or bonded. Or bonding electrons. Those are the ones. So let's say you have a tug of war between two atoms in a bond. Who wants the electrons more? You can think about unequal sharing between two atoms, and I'll talk about that more in a second. So some electronegativity values that you've got to memorize. I would say you need to memorize all of these ones, okay? And then you should memorize hydrogen. So I'll put here memorize. Before you get intimidated, if you remember that fluorine is 4.0, as you go backwards, you just drop half a unit. So to 3.5, to 3, to 2.5, to 2, to 1.5, to 1 at lithium. So you just keep decreasing by half a unit. Hydrogen is 2.1. That's one you just kind of have to know, but it comes up a lot in organic chemistry. Another rule I could teach you is the down 1 and over 2 rule. It only applies for a couple of elements. But if you know carbon, which is 2.5, if you go down 1 and over 2, sulfur is also 2.5. That rule also works for nitrogen. You go down 1 and over 2, so chlorine. It's close for boron. So for boron, you go down to phosphorus. It's close to 2, but it doesn't quite work. It doesn't work as well for beryllium or lithium, but it works for carbon and nitrogen pretty well. Other little trends, I don't know if you would have seen these in Gen Chem or not, or if you figured them out on your own, is that if you go to the third period, once you get to the third period, it kind of goes up by 0.3. So 0.9 to 1.2 to 1.5 to 1.8 to 2.1. But then it doesn't follow that trend. It goes up by 0.4, so 0.4 and 0.5. But if you remember the down 1 and over 2 rule, then you'll know sulfur and chlorine anyway. So it only works up to phosphorus. That's another one that you can kind of use. What else? You can make up your own mnemonic, I guess, or maybe a song or a rhyme or something to help you memorize them. But again, the ones that I need you to have memorized for the first quiz would be these ones. So second period and hydrogen. Those would be the most important in this class. There you go. So some quick and dirty rules about memorizing electronegativity values. Well, let's talk about the 3 types of covalent bonds. You can have a covalent bond that is what we sometimes call a non-polar covalent bond. You can have what's called a polar covalent bond, and then you can also have what's called an ionic bond. So you need to know the difference between all three of these. A nonpolar covalent bond is one where you have a difference of electronegativity between the two elements that are sharing the electrons. When the difference in their electronegativity values is less than 0.5, it's considered to be nonpolar. Let's just try some math here. If you have two carbon atoms like this one, so you would put delta En, which stands for the difference in electronegativity, is equal to carbon is 2.5, and then you subtract the other carbon, 2.5, so that gives you 0. So 0 is less than, 0 is less than 0.5. Therefore, this is non-polar. Same thing would apply here between carbon and hydrogen. You would do delta En is equal to 2.5, subtract 2.1, which gives you 0.4. So there's some difference, but it's still, we're kind of running out of space here, but it's less than 0.5. Therefore, this would also be non-polar. For a polar covalent bond, we see a lot of carbon-oxygen bonds in organic chemistry. If the difference in electronegativity falls between 1.7 and 0.5, it's considered polar. So let's try this one here. You got delta En, oxygen was 3.5, carbon was 2.5, so that gives you 1.0, and that falls within this range. Therefore, this is a polar covalent bond. And then if you go to sodium hydroxide, here you would start with the oxygen, which has an electronegativity of 3.5. In sodium is only 0.9. And so that gives you 2.6. So 2.6. And so 2.6 is greater than 1.7. And therefore, this would be considered ionic. All right. And so you got to know the difference between nonpolar covalent, polar covalent, and ionic bonds. Now, in this class, we don't look at lots and lots of ionic bonds, but the reason why polar covalent bonding is so important for us as organic chemists is because when you recognize polar covalent bonds, it enables you to be able to look at a molecule and say, okay, this is going to react this way. This is going to react at this atom. This atom is going to react in this manner. Okay, we're always looking for regions of high electron density and regions of low electron density. So how do we represent that? Well, you might have noticed these little delta symbols here. What the Greek letter delta represents is partially. Okay, it means partially. And so when you see delta plus, it means this carbon is partially positive. It means that this oxygen is partially negative. They're not a cation and anion respectively, but the carbon and the oxygen are sharing the two electrons in this bond. However, the oxygen is taking more of the electron density. The analogy I would use for that is sometimes I like to go to Costco with my daughter, she's 7, and we'll share a slice of pizza. Are we sharing? Are we sharing? The answer is yes. Is it equal sharing? The answer is not really. Okay, Dad is probably getting more of the pizza. It doesn't mean that we're not sharing it, but one is getting more than the other. And so the two electrons that are found in this bond, okay, most of the electron density lies to the side of the oxygen because it has a greater ability to pull electron density towards itself. And that's what the definition of electronegativity was. It's how strongly an atom attracts those shared or bonded electrons towards itself. And so beside using the delta symbols here, we can also use an arrow with a line going through the end that is opposite of the double barb, or the whatever you want to call it, the arrow, okay? If you use that line, that's what we call a dipole arrow, and that means the exact same thing. This side is the side where the electrons are found in, there's a greater density of electrons. And this side, I kind of remember it, if you put a circle around it, it looks like a positive, right? And so this side is going to represent the side that has less electron density. I'm sure you would have seen these arrows in your general chemistry class. Now take a look at something like a bond between carbon and lithium. We have CLI. You see that in the top structure, I have it drawn with a dipole arrow, and it looks like there's a covalent bond between the two. But over here, you see I have a negative charge and a positive charge on the carbon and lithium, respectively. Well, if we calculate the difference in electronegativity between the carbon and the lithium, carbon is 2.5, whereas lithium is 1.0. That gives you 1.5. Now, what was our cutoff? We said that the cutoff was 1.7. Now, this number is less than 1.7, but it's also kind of close to 1.7. So sometimes we'll look at a bond that just if we were to take the rules as hard and fast, we'd say, well, that bond is going to be covalent. And in some circumstances, we'll treat that bond as if it were ionic. Now, if you're wondering, are you going to try to fool me with that on the first quiz? The answer is absolutely never. I would not do that on the first quiz. But the idea is that the rules for something having a difference of electronegativity being less than 0.5, if it's from 0.5 to 1.7, and if it's greater than 1.7, as being covalent, polar covalent, and ionic, these were not rules that are law, okay? These are just numbers that were developed by human beings to give us an idea of the character of a bond. And so sometimes you have to take it with a grain of salt, and you're going to say, well, even though it has, looks like a polar covalent bond, I can treat it as if it's ionic. And I have that summarized on this slide right here. And so to summarize, sometimes it's acceptable to write a bond as covalent or ionic, depending on the situation. And again, you have to take electronegativity with a grain of salt. Again, I am not going to try to fool you on your quiz. Okay, that's not the point. The point is to understand that sometimes you can treat a bond as covalent, sometimes you can think of it as ionic. But for the first quiz, we will use the rules hard and fast. Less than 0.5, non-polar covalent. Between 0.5 and 1.7, polar covalent. And greater than 1.7, we'll consider it to be ionic. Well, with all that spinach or all that information in mind, let's see if we can identify some polar covalent bonds in a couple of compounds. So we've got an interesting compound. I'll zoom into it here. You've got hydrogens, carbon, you got a fluorine and a chlorine. Could anybody tell me which one of these, or which one of these bonds, I mean, there's 4 bonds. If I highlight this one in yellow, this one in blue, and I'll highlight both of these in green because they're both carbon-hydrogen bonds. Could anybody tell me which one of these bonds would be a polar covalent bond? Which part are you confused about, Andrew? So I see that Luke has identified one of the polar bonds. Okay, I'd say that the yellow bond is polar, right? So Andrew, I'll try to re-explain it here. So we want to know if this yellow bond, is it polar? So what we do is we calculate the difference in electronegativity. The triangle means delta, which is difference. Right? Just like in general chemistry, you would have seen delta H, which is difference in enthalpy or change in enthalpy. So we have the difference in En, which is electronegativity. Like that. So we have a fluorine and a carbon. Fluorine has an electronegativity of 4.0. Carbon has an electronegativity of 2.5. So 4 minus 2.5 gives us 1.5. We said that if your bond difference in electronegativity is between 0.5 and 1.7, it is considered to be polar covalent. Covalent. And thus, this would be a polar bond. So we'll put here polar. All right. What about the bond between the carbon and the chlorine? What about the bond between the carbon and the chlorine? There we go. Yeah, I see that somebody put that it's polar. So we have here the difference in electronegativity. Chlorine has an electronegativity of 3.0. Carbon is 2.5. And so we end up with 0.5, which falls in the range of 0.5 to 1.7. And therefore, it is a polar bond. Both of these bonds, the bonds between carbon and hydrogen, are non-polar. We already looked at this. The difference in electronegativity is going to be 2.5 minus 2.1, which gives you 0.4. That's less than 0.5, and therefore they are non-polar. So Andrew, going back to your question about carbon and lithium, okay, if we look at the rules and you look at the difference in electronegativity between these two elements, it would be a polar covalent bond. And so you would say that this is delta negative and the lithium is delta positive. However, in some cases, we will treat it as if it's an ionic bond and help us in order to help us to understand reactivity. That's all it means. So again, following the rules, it is polar covalent. However, some cases we'll look at it as ionic, but we're not going to cover those in chapter 1. That's something that we look at much later. So for now, you can treat it as if it's polar covalent. All right. What about E? Are there any polar, or are there any covalent, are there any polar covalent bonds in here? This molecule, this is acetone, which is sometimes used as a paint thinner, nail polish remover, acetone. Any polar covalent bonds in this one?
Can you go back to the previous one? I couldn't see it and it was fast. Thank you. I just need to take a picture.
So remember that all of these slides are posted to Canvas. Everything is posted to Canvas. Yeah, the bond between the carbon and the oxygen is a polar bond, right? You have a delta negative here and a delta positive here, because if you look at the difference in electronegativity between those two elements, oxygen is 3.5 and carbon is 2.5. That gives you 1.0, and that falls in the range of 0.5 to 1.7. And so this double bond is polar covalent. Polar covalent bond. Give me a thumbs up if you follow me on polar covalent bonds and you're able to identify them. Cool. There are no other polar bonds anywhere in E. The only one is that double bond between the carbon and the oxygen. So I'll highlight it in yellow. The only polar covalent bond in there. The next section, 1.6, deals with atomic orbitals. And so we're going to talk about a little bit about s orbitals, p orbitals. Those are the only ones you'll see in this class. D orbitals and f orbitals don't really come up in organic chemistry 1, like the shape of a d orbital, or definitely an f orbital. That certainly doesn't show up. But in this class, you need to know about s orbitals and p orbitals, right? If I was to, show you these 4 orbitals that are drawn down here, could anybody identify which one is an s orbital? If I call this 1, 2, 3, and 4, could anybody tell me which one of these is an s orbital?
Number 1.
Yeah, the first one is an s orbital. The other 3 are all p orbitals, py, px, and pz, respectively. Yeah, so you need to know the shapes of orbitals, and you need to know about sigma bonds and pi bonds. But one thing you'll see about our book is that he goes into a little bit of detail about quantum mechanics. You don't need to know anything about quantum mechanics in this course, okay? It doesn't come up except for in the first chapter. And there's nowhere in this class that I'll be asking you anything about quantum mechanics. So don't really stress about that. So why don't we take a short break, and then we'll come back and we'll take a look at atomic orbitals. Boom.